Hello. So in today's video, we are going to understand the concept of basis vector and dimension for a linear system, and if possible, we will try to discuss the concept of quotient space. So first of all, let me write down the definition. Let capital X be a vector space formed over a field K, and let you are having x1, x2, xn be the elements of capital X. Now, if there exist constants like a1, a2, an, all the constants belong to field K. Why they need to be belong to field K? Because we want to exploit the property of scalar multiplication of the vector space here. However, so if there exist constants, those are not all of them are equal to 0. A few of them may be equal to 0, but all of them are not equal to 0. Such that this is very important equation. Actually, I am going to present the definition of linear dependent vector such that now let us number this equation as equation 1. So then we will claim x1, x2, xn are linearly dependent Now, what is linearly independent? Like that is not, if all these x1, x2, xn, all these vectors are not dependent, that are linearly independent, or in other way, in terms of mathematics, you can say that for linearly independent equation 1, linearly independent vectors may satisfy equation 1 provided all the scalars a1, a2, an are is equal to 0, right? So now let us try to understand the lemma. So you can say that a set of vectors x1 to xn are is linearly dependent if, means if and only if one of them anyone like x1 x2 x3 xn, any one of them as a linear combination. Equation 1 was an example of linear combination of others. So let us consider the proof. Suppose a vector xi is linearly means expressible by means of linear combination of the remaining n minus 1 vector. So we can write j is equal to 1 to j is not is equal to I. It is ajxj, right? Now what we can write here, that we can add xi to the both side, minus xi to the both side of this one. It is easy to claim that minus xi will also exist because xi being an element of your vector space, xi must have an additive inverse exist in your within your space x. So that minus xi will also exist inside that space. So my xi minus xi this, and reach the end of the page. So what we will get that 0 is equal to ajxj minus xi j not is equal to I, right? Because if you add your vector with so this implies that further we can write this as like, if these are the case, so this further can be written like or let us change this because otherwise you will get confused. In xl is equal to 0 where al is equal to minus 1, right? So this proves that this combination And the converse can also be proved, like if x1 to xn they are linearly dependent, then we can write n I is equal to 1, ai xi is equal to, or better to write so where right, so we can always write that we can obtain the ai, like if we want to express one vector by means of other, then we can take ai xi this side and write it like so xi will be minus by ai. So now we can conclude one important thing, that if there exist n linearly independent vectors in a vector space, then we can say that the degree of freedom of that vector space, or that dimension of the vector space, is at least n. Now, what we can say, that if we can find out a finite n, finite capital N, that indicates the degree of freedom or dimension of the vector space, then we will call this vector space as a finite dimension vector space. Like inside, we can rewrite it in different way, that in capital X, if we can find out at max n numbers of vectors that are linearly independent, then the dimension of capital X is n, and if n is a finite number, then X is considered as a finite dimension vector space formed over the field K. Now, one thing I would like to tell you in this context, that do remember your vector space dimension has a close relation with your means field, on which the vector space is formed. Because let me just give you a simple example. If you consider C, the set of all complex numbers and R, the set of all real numbers, you will find that both of them are filled by their own nature. However, if you consider the C, if you consider vector space C over R, you will find that its dimension is, means we can write C over R, the dimension of this is 2. Why 2? Because you can intuitively understand this one. Like your real number, you will have any number. Now, if you want to express any element of your complex number system, that is a vector space over R, the set of real number, then what do you need? You need two components, like you need one R to represent its real part, another R to represent its imaginary part, right? Like two individual numbers has to be picked up, from your set of all real numbers to construct its basis, right? So it is a two dimension. But if you consider that it is one dimension, because one is sufficient for you to represent any vector. Now here the one thing you must make sure that your basis element of your basis vector must be picked up from your field, and that is why there is a change in the dimension. That here I am not talking about by means of these elements, I am not talking about the vector elements, rather the scalar elements that present in the construction of your basis vector is basis vector element of the field K on which your means space formed. So in future I will talk more on that, and when I will try to show that what is the essence of finite dimensional vector space and infinite dimensional vector space. Like if you consider the vector space formed by the set of real number over the field of rational number, then you will observe that it is easy to prove that R, the dimension is infinite, and when we will discuss more on the non-linear space, it is not non-linear space, it is non-linear space, then I would like to discuss all this in detail. However, here let us take a few examples, or before we take example, let us take another definition that is going to be important for our future analysis, like let x be a finite dimension functional vector space over the field K now over the field K, then what we can write that a family that is that comprises v1, v2, all these are vectors. Is a basis of x if they fulfill the following two conditions, like obviously they have to be linearly independent. And the second one is obvious, like obvious augmentation of the first one, that appending any other extra vector will make them dependent. So that is very interesting thing. So let us try to understand what I am trying to say by this. Like if like x belongs to x and there exists a set v1, v2, vn such that vi belongs to x for all I 1 to n, right? So what I am going to do, I am going to add it here. So it will become x comma v1, v2, vn. So what is my claim? That this one, although this one was linearly independent, however this one becomes linearly dependent. So how we can show this? Like if if v1, v2, vn they are linearly independent, then x another vector that must be expressible in the combination of v1, v2, vn, or what we can write in terms of mathematics. Just check it because I am writing all from my mind, and it may so happen that I make some mistake. So don't trust whatever I am writing on this video, but on the screen. Rather, you should apply your brain and try to analyze each and every facts that I am going to present here. And if A is equal to 0, they themselves were before appending x to that set, they were linearly dependent. So we can't help them to become linearly independent. And then obviously the other case is that A is not 0, and you can represent them in form of your basis vectors. Now that one thing is here I would like to mention, and it is very common in your real life, like if you consider the three-dimensional space. Those who are having that undergraduate electromagnetics, they must have noticed that while calculating fields for different objects that are maintaining or possessing different symmetry, we apply different coordinates. Like in case of parallel plate capacitor, the field in parallel plate capacitor, we prefer rectangular coordinate, while for like magnetic field due to a current carrying conductor, we prefer cylindrical coordinate, while calculating the like short line charge field, we prefer cylinder like spherical polar coordinate. So all these three, so what I am trying to say here, basically for 3D space you can have three different type of representation. One is that Cartesian, or not Cartesian, you can say it is a rectangular coordinate system. Obviously that forms a means that XYZ, they forms a basis vector of your so how should you write it? It should be like 1 0 0 0 1 0 another form of representation is cylindrical coordinate. So it is an example of cylindrical polar coordinate. Unfortunately, that diagram is slightly hazy. I'm trying to show you possible. Yeah. So this is an example of cylindrical polar coordinate. Now, if you take this one, that r theta z, they will also form the basis of a vector space, right? They will also form the basis of the vector space. So here one is this one, another one will be r theta z. Similarly, if you consider that spherical polar coordinate, then in spherical polar coordinate also you can see that here it is given that your basis can be represented by r theta means psi and nu. These three can be. So what is my point is here is very simple, that for a 3D space you need three orthogonal vector. It may so happen that they are means magnitude wise they are one, so they will form an orthonormal set. That's a different story, but orthogonality is required, means the three vectors must be linearly independent, and they are means irrespective of your choice of your basis. That choice of basis dependent on your choice of your coordinate system or your representation, whether you are means which type of representation you are trying to reach. So that makes a difference in your choice, but obviously the number here also it is 3, like 1 it is 1 2 3, and obviously in case of your r phi z you will find there is also 1 2 3 three vectors are required. Those are linearly independent, or we can say they are orthogonal to each other to represent this space. Now another thing is very important, that like I just forgot what I was trying to say. Just give me a minute. Yeah. So what we can say, I was trying to show you a lemma, that let x be an n-dimensional vector space, and is a basis for x, then every element of x can be expressed as a unique linear combination of So what I am trying to say, let x be an n-dimensional vector space, and E1, E2, En, all of them, they form a basis of that vector space. Then like any element of x can be expressed as a unique combination of linear combination of this vector. But do remember that this representation is unique with respect to your choice of your basis, but it is not unique with choice of, like A single point in space can be represented in thousand different ways. It only depends on your choice of your unique vector. Like let me take an example of a two-dimensional vector that will be easy for us to visualize. Like you are having here, it is 3 comma 4. So there are many ways. Let me write a few bases of this space, like 1 comma 0, 0 comma 1, then 2 comma 0, 0 comma 2, then 1 comma 1, and like 2 comma 3. Obviously you can see that whatever I am writing here, they are linearly independent of each other. Like this is a set of basis vector, this is a set of basis vector, this is another set of basis vector. You can have another set like so obviously here when you are trying to represent 3 comma 4 with your first basis, then it should be like 3 1 comma 0 plus 4 0 comma 1, that would result in 3 comma 4. However, when you choose your second one, that will be like this. However, what I am trying to say, when you are selecting your second basis, these 1.5 and these 2, they must be constant for your representation, as long as you are considering this particular point. You are trying to, this is an element of means R2 vector space formed over R, and you are trying to represent its element by means of a particular basis, like 2 comma 0 0 comma 2 is a particular basis. Then this selection of this scalar means scalar must be unique. You cannot have here any other combination other than 1.5 or 2 that would result in these 3 comma 4. That is what I was trying to claim by that previous statement. Now what we want to and in this way what we can say that is very important for us, for our control system also. X becomes isomorphic to K as a vector space, right? I will try to elaborate, plus let us try to prove this one. So by the definition of basis, your if you punch, or if you just means append that element x that you want to represent by your basis vector within their set, then it will be like this set must be linearly dependent. Now what we can say here, that x is x can be expressed as a linear combination Now here is the twist. Let us consider there exists two such representations. Both of them will be sum of n number of terms, like n is equal to I1, this be AI, EI, and another sum, that is n j is equal to 1, that is Bj, Ej. Or you can say like let it be I, otherwise we will be in trouble. Only we are claiming that we are having the same basis vector like EI to EI, but what we are trying to prove that AI and BI, they are cannot be different, like AI is equal to BI, what we want to prove for all such value. So what we can see here that like as x is a vector and that is expressible in this way, so what we can do is like I am here doing a few step jumps, like what I am trying to do here. It's very simple. Oh God, I have reached again the end of this page. Whenever I try to do some derivation, then only this problem happens. So we started from here that x is equal to n, I is equal to n1 in. So we are having, suppose a, we are trying to prove it by contradiction. Like let us start with a not is equal to b, meaning ai not is equal to bi. Now what we are claiming that even if they are not equal to each other, but we are having x, the same vector can be expressed by two different representation with same choice of basis, right? So if they are same choice of basis, now here I am doing a few step jumps, like instead of doing that I should do it step by step, like this x, we can write it like x minus x, and here also it will appear in this summation running from I is equal to 1 to n ai ei minus x. Now instead of minus x, in the next step we can replace that x by summation of I is equal to 1 to n bi ei, right? Then this will result in this stage. Now x minus x by the virtue of vector space means how we define that structure. Whenever we subtract one element from that same element, it will result in the null vector. This 0 is not 0, this is null vector. So if it is n dimensional vector space, this is actually 0, 0, 0, all these 0, right? Okay. Now what I am trying to say here, so if that is the case, then what we can see that it can be written like using the property of, just a minute. Now as both of them are representing a vector element x, so we can expect that we can apply the distributive property, and that application of distributive property will yield that it could be written like ai minus bi ei is equal to null vector, and as ei they are not trivial, so obviously it implies that ai minus bi, this scalar is equal to 0, that indicate that ai is equal to bi for all I is equal to 1 to n. Right. So the representation is unique and no other representation can be found there. Like if you consider Rn, the natural basis, what I already discussed, that it is for R3, natural basis is E1 is equal to 1 0 0, E2 is equal to 0 1 0, E3 is equal to 0 0 1, like that. Even we can show that the vector sin t comma cos t, they forms means they also constitute a basis of a two-dimensional space. Okay, so one more thing that another lemma instead, I may not be able to prove. You have one theorem is the basis of that theorem is very simple thing. What it states, that theorem states that if you have a vector field x, and let me write it completely. Let x be a vector, not vector field, be a finitely generated vector field vector space formed over the field K, then X has a finite basis and any basis of x have same number of elements. I have already discussed this for three-dimensional space. We can have our rectangular coordinate, we can have cylindrical coordinate, we can have spherical polar coordinate, but for all the coordinates one thing remains same, that is the number of elements in that vector space. So it's true. Now another thing is that I have already discussed finite and infinite vector space. Let us consider only a few important corollary, like if a vector space Vf is of dimension n, then important corollary, let means if a vector space X, if a vector space capital X is of dimension n, over the field. I repeatedly tell you that please do mention the field, because if you change the field, then all the other definitions will be changed and your vector space dimension will also vary. Right? Then any n numbers of linearly independent vectors in VF can in X can form a basis of X. That is very important. Like if you consider the rectangular coordinate, then you must have noticed that there are three vectors, and what was the dimension? It was R3, like three-dimensional vector space of real number formed over the field of real number. So these three basically it gives us it evokes an impression of the square matrix. Like if you have n number of elements, you need means if your basis vector has n number of element present in this, then it is and you need n number of vectors to means form your basis. Then it is any n vector, any n number of linearly independent vector can form your basis. Like if you have that rectangular coordinate, you can have that with polar coordinate, spherical polar coordinate, you can have that with cylindrical coordinate. So that is an important one. And last but not the least, let me write the another important corollary, that for any subspace W of a finite dimensional vector space capital X is always like dimension of W is less than is equal to dimension of X, and further we can only claim W exactly equal to X when dimension of W is equal to dimension of X. You should try to prove it by yourself. And one that is the other corollary or theorems are very easy to prove, so you can do it by yourself.